the first section we're going to look at this week is 6.3, part 1. Then we're going to do part 2 tomorrow. We'll do part 3 on Thursday. So no review day this week, but I think you'll find this stuff is probably pretty easy. So we're going to be looking at graphing those two functions. And we haven't really looked at any functions that are going to look like this one. And we've looked at lines, we looked at parabolas, so like quadratics. We've done square roots. We've done exponential functions, log functions. We've done all those different kinds of functions. None of the functions that we've studied so far have been what we call periodic. All right, let me just graph one so you can see what it looks like. All right, so sine of x. Actually, before I even hit graph, does anybody know what the graph of sine looks like? Yeah?
It looks like, I guess, like a wave.
Yeah, it's going to look just like a wave. And a lot of times when we do graphing, we usually do zoom 6, and that sets a window of -10 to 10 on the x and the y-axis. We're going to do zoom 7. Okay, under zoom 7, it says zoom, and then it says trade. When we're graphing things that have sine or cosine in them, zoom 7 is usually the one we want to use. And that's what it looks like. Okay, that's the graph of sine. Let me take that. Put that right there. So if you look at it, it keeps repeating itself. Right? Parabolas or lines or things like that, when you draw them, they don't repeat. Like when you draw a parabola, it doesn't look like this. It doesn't keep repeating. There's one parabola, and then that's it. But a sine wave repeats itself. So we start here, we end there. What I just traced in red, that's called one cycle of the graph. If I took that section and I copied and pasted it forever, left and right, that would be the entire graph. I can take that, put it right there. There you go. That's the next cycle for the sine function. So that's why it's called periodic, because it repeats itself. The y values never go above 1 or below -1. This is 1, and that's -1. They start at 0. The highest they go is 1. Then they go back to 0. The lowest they go is -1 and back to 0. So that pattern of 0, 1, 0, 1, 0, -1, 0. Those numbers keep repeating themselves. And that's what makes it periodic. The y values keep repeating themselves. In the same order. Okay, that 0, 1, 0, -1, 0. That's the sequence of the y values for the sine function. There's other y values too, but what I'm giving you is the beginning, the high, the middle, the low, and then the end. Those are the 5 values I gave you. Now I say that the y values repeat themselves over a given set of x values. You have to travel far enough before they'll start repeating. Like if you just go from here to here, well, you haven't gone far enough to see them repeating yet. To see them repeat, you have to go from there all the way to there. This distance that I just drew in green, that's the amount of distance you have to travel before you'll see it repeat. And that distance has a name. Here I just say over a given set of x values. I'll tell you what the name is in a minute. Now, we can change that. So if you look at it on the screen, basically from here to there is how far it has to go before it repeats. Now, if I do this, did I just increase the amount of distance you have to go before it repeats? Or did I decrease it? Yeah? I decreased it. So now you only have to go from here to here. That's much smaller before you see it repeat. And we'll talk about what that's called in a little bit. But the idea is we're going to look at how can you transform sine and cosine. How can you shift them up and down, shift left and right, stretch left and right, which I just showed you, and then stretch up and down. So we're going to look at transformations. And all the transformations we look at are exactly the same as everything we've studied all year. There's no difference. So how long is that interval that you have to travel from here to here before it repeats? Well, if you stretch or compress it, you can change it. But if you don't stretch or compress it, it's 2 pi. 2 pi is the distance you have to travel before the graph repeats itself. If you don't stretch or compress it. Does anybody remember what 2 pi is the same as in degrees? Yeah? 360 degrees, yeah? So the idea is if you travel 360 degrees on the x-axis, after that, it's going to repeat itself. And 2 pi is going to be the length of the interval before the graph repeats itself for every problem we do today and every problem we do, I'm trying to think if it will be tomorrow. Well, definitely today. And I told you that that length has a name. I already referred to it as one thing. I called it a cycle. But it's also called, probably should have underlined it, a period. The period of the graph is the amount of time before it's going to repeat. But if you hear me ask a question like what's the period of the graph or the cycle, those two words mean the same thing. Period and cycle. Now, what would you do with sine and cosine? There's a connection I can do with sound. So we'll play some different sound frequencies just to show you kind of one application of this stuff with sound. Sound is kind of a neat one to do because you can hear what's happening. There's other applications, but it's kind of hard for me to demonstrate it. But sound is pretty easy. I can do that. Okay, so what is this distance called from here to here again? Not how long is it, what's it called? Yeah.
A period?
Yep, this is called 1 period. I'm just going to write that in there. That's 1 period of the graph. Which is also known as a cycle. Yes?
Do you measure it at that point of the wave every time?
You can really measure it anywhere you want. But the idea is I usually start right at the origin and then go from there. Yeah. But if I don't think these green lines will stay together. No, they don't. But if I could move them together, anywhere that I put them would be looking at 1 cycle. But yeah, we usually start right at the origin. So when we want to graph a sine or a cosine wave, you don't have to graph the wave forever. It's going to take too long. So all we're going to do is graph 1 cycle of the wave. Because my thinking is if you can graph 1 cycle, then all you'd have to do is copy and paste it. You could do 2 or 3, however many you want. Since it's a wave, it's a little more complicated than a line. Like a line, you only need 2 points. And you can get a nice picture with it. With the wave, you need 5. And the 5 points are going to be the beginning, the end, the middle, the high, and the low. If you graph those 5 points, then you can get a pretty good picture of your wave. Let's go back here for 1 second. How long did I say one period was? 2 pi, or what about in degrees? 360. So when you put 5 points, think about how many sections you just broke that wave into. Do them in different colors. So we got first section. So that's section 1. There's 2. I'm just connecting the lines between the points. Here's section 3. And the last one, here's the 4th section. So when you put 5 points, you break it into 4 sections. And we're starting at 0, and we're ending at 360. So how much do you think each tick mark is on that graph? It's not 1. It goes from 0 to 360, and it's broken up into 4 pieces. Yeah?
90 degrees.
Yeah, exactly. Each one of these points is 90 degrees further down than the one before it. We're going to be using radians. So in radians, we would say that all these x values are pi over 2 radians apart. And that's the same graph I just had on the other page. I just labeled everything. So 0, 90, 180, 270, 360. In radians, 0, pi over 2, pi, 3 pi over 2, 2 pi. And if you're wondering, like, why is it a 1 and a 0 and a negative 1? Well, we can just type it in on the calculator and I'll show you that. Yeah.
What was the way of measuring the radians? So, like, that's the radian form. What's the other way? In degrees. How does it go?
Yeah, you can measure. The x-axis represents an angle. So you can measure an angle either in radians or degrees.
So, in degrees, would it just go up by 90 degrees? Or?
Each tick mark represents 90 in this picture.
Okay.
I'm not saying every single graph you ever see represents 90. I'm using 90.
Sure. But in that case, as you go up, it's going up 90 degrees.
They're going up by 90, yep.
Okay.
All right, let me put my calculator in radians. It already is. And let me type in 0. If I find the sign of 0, it's 0. When I hit enter, it's giving me the y value. What I plug in is the x. The answer I get is the y. Let's do sine of pi over 2. Pi over 2 is the x. When I hit enter, it's going to give me the y value at pi over 2. What does it look like the y value is in that picture? Yep. 1. That's why it's 1. If we do 180, sine of pi, pi is the x value. That's what I'm plugging in. When I hit enter, I'm going to get the answer. What does it look like the y value is at pi? Yep. 0. And we could go through and check all of them, but if you plug in 3 pi over 2, you get negative 1. And if you plug in 2 pi, you get 0. So that's where those numbers are coming from.
Where do those values of those radians, do they each belong to a segment? Or like from the first point to the second point, is that pi over 2? Or is that the whole?
So it's just marking the, like if you had graph paper, it's just marking the lines on your graph paper. Usually graph paper goes by ones. We're just going by 90s.
So it's not the points, it's the, like, never mind.
So it's just like, if you had something like, you did something like this. And you had a point like right there. It's just marking the x value of that point. So this is 2, 1.
Yeah, I got it.
All right, so when we want to graph a transformation, the important thing we have to know is where did it start from? Because if you don't know where the original one starts, and I say like shift it up 2, you're not going to be able to shift it up 2. unless you know where to start from. So I'm going to give you two tables, one for sine and one for cosine, that basically describe this picture. Okay, we've pretty much already done it for sine. So I'm going to take the 5 points you see right here, and I'm just going to write them in a table. So we've got 0, 0. Pi over 2 is up at 1. Pi, the next one is going to be at 0. Three pi over 2 is negative 1. And 2 pi is 0. This one is really a repeat of that. They're the same one. It just depends on how you think of it. This is the end of the first cycle. It's also the beginning of the second cycle. It's where the first one ends and the second one starts. Now, what we haven't looked at is cosine. Okay, that is also a wave, but I'll give people a second to copy that, and then I'll show you what that one looks like. So every problem we do that involves graphing this week, that's the table you have to start with. And then depending on what we do, we're going to modify these x's and y's. Like if we're going to shift it up or down, we would modify the y's. If we're going to shift left and right, we would modify the x's. Let's look at cosine. So let me put sine back the way it was and cosine. So these two graphs I'm going to show you, these are the original graphs without anything done to them at all. No shifting, no stretching, nothing. Okay, so there's sine. And red is cosine. What's all right, let's put that over here. So what's the difference between sine and cosine if you just look at the picture? Yeah.
Just transform the unit over.
Yeah. And what do you remember each one of these tick marks represents how many degrees? 90. So it's one tick mark over, which means sine and cosine are horizontal shifts of each other by 90 degrees. So for cosine, we're going to start at 1. Then we're going to go to 0, then we're going to go to negative 1, 0, and back to 1. Those are the first 5 points in the cycle of cosine. 0, 1, 0, negative 1, 0. And that's what I have on the table. I'm sorry, 1, 0, negative 1, 0, 1. I don't know why I said so. So starts at 1, down to 0. The lowest it goes is negative 1, then back up to 0, and then all the way up to 1. Because we only sketch one cycle when we draw it, the cycle that we sketch for cosine is generally what's inside that box. It's going to look more like a V shape. For sine, it looks more like that wave shape. They're both waves. It's just a matter of what section we're sketching, because it goes on forever. So we have to decide what we're going to sketch. And we always sketch what's inside that box. Anyone's going to copy down those Just two tables. Alright, so we're going to do a problem about sine. Like if I asked you to graph something like this. Sine of x plus 2. Hopefully you know what this plus 2 is going to do. It's adding a number on the end. So we've talked about how that moves things. But since it says sine here, you're going to use this table. If it said cosine here, you'd use this table. For the x's, it doesn't make a difference which table you use because they're the same. But for the y's, it does. So when we've done transformations in the past, usually we just jump right in and we do pretty much all of them in the same day. Well, we're really going to kind of break this down. And we're only going to do 2 transformations today, and then we'll do the other 2 tomorrow. And the types of problems that I give you to start with are only going to do 1 transformation at a time. Okay, so what do I mean by that? There's a transformation that does one thing to the sine function. It shifts it up 3. There's another transformation. That's a vertical stretch by 2. And that's it. It's the only thing it does. Just one transformation. Let's do... I graphed one like that earlier to you when I wanted to show you the graph getting compressed. That's a horizontal stretch or compression. And that's the only thing that's happening. An example of 2 things happening would be like this. Well, now you're doing 2 things. You're going to do some stretching or compressing and some shifting. We're not going to look at problems today or tomorrow that do 2 things in the same problem. Only one thing per problem. And because we're only going to look at 1 transformation per problem, that means 1 column for that original table I just gave you is always going to stay the same, and the other one will change. So let's think about like something that shifts up and down. If we shift up and down, think of a coordinate. What value of a coordinate would be affected by shifting it up or down? The x or the y? Yeah, the y. So if we shift something up and down, the y value would change, and the x column would stay the same. Now, if we do 2 things at once, we might change both columns, but we'll save that for probably like Wednesday or Thursday. All right, so that's pretty much all kind of the background information for graphing sine and cosine. Now, the rest of today, we're going to focus on how to do 2 specific transformations. And today will be the shifting left and right, and then shifting up and down. Question?
What would the language be like for shifting up and down?
We're going to go through and I'm going to give you like a template. I'm going to show you what you do to shift up and down.
Okay.
That'll be the second one. The first one we can do, shifting left and right. Now, first thing is, they give it a little bit different name. How it works is exactly the same way every transformation we've studied all year works. But when you shift left or right, they call it a phase shift. And does anybody remember, when you do shifting left and right, or shifting up and down, does that involve adding and subtracting? Or does shifting involve multiplying? Yeah? Right. Adding and subtracting is how you do a shift left and right or up and down. When we shift left or right, where do we add or subtract? Inside the function or on the end of it. Remember? Yep.
On the end.
So like,
Inside.
if you had like something like this, would that shift it left or right 3?
That would be up.
That'd be up 3.
Yeah.
So when you put it on the end, that's up and down.
Yeah.
When you put it inside, that's left or right. And what inside means for this kind of problem is it's inside parentheses. Remember, this whole thing, that's called the argument. We talked about arguments a lot when we did logarithms, and a lot of times we said like the argument ends up by itself because it argued with everybody. That's not really happening here, but this thing is still called an argument. So when you shift left or right, you add or subtract a number to the x value first, then take the sign last. Which way do you think plus would shift it? Would plus shift it to the left, or would plus shift it to the right? Yeah, to the left. Yep, plus is going to shift it to the left. And that means minus is going to shift it to the right. Now, how much is it going to shift? Well, it depends on what this number is. When we've done shifting left and right before, we've just shifted by any number we wanted. And you can do that here. I mean, if you want to shift it by 10.6, I mean, you could do that. But I'll tell you the most common numbers that we shift by in degrees are 45, 90, and 180. That's usually what we shift by. So in radians, you would see pi over 4, pi over 2, and pi. It's 45, 90, and 180. Yeah, just wait for this. Okay. So, if we shift left and right, what part of a coordinate does that change? Moving something left and right, does that change the x value of it? Or does that change the y value? Right, the x value is going to change, which means in this case, the y stays the same. Yes?
Can you scroll up a little bit? I get to
So that's what we'll write down next, that the x column is going to change, and the y column is going to stay the same. Right, so I mentioned before, when you want to graph one of these, you need 5 points. So the first thing you're going to do is you're going to go down, or if you have a reference sheet for the test, you're going to look at your table for sine. In the table that I gave you for sine, you're going to copy down the y values because they stay the same. When you shift left and right, you're not changing anything up or down. Well, if the y's are going to stay the same this time, then that means the x's are going to change. I'm going to tell you how they change, but I want to go look at the next problem we're going to do and ask you a question about it. And then we'll come back to writing step 2. Okay, so we're looking at adding and subtracting inside the parentheses. So don't copy it yet because we still have to finish step 2. There's a minus pi over 2 inside the parentheses. Which way is my graph going to move? Because I have a minus inside. Yep.
To the right.
It's going to move to the right. What happens to x values as they move right? Think about like a point moving to the right. What's happening to it? Yep.
They increase.
The x value is increasing. So when you see a minus pi over 2, you know it's going to the right, and you need to make the x bigger. How much bigger? That much bigger. So what ends up happening is you do the opposite of what you see there. If you see a minus pi over 2, you're going to do a plus pi over 2 to shift all your x's to the right. If this was a plus inside, that's going to move them to the left. What happens when things move to the left? The x value gets smaller. So if you see a plus here, you need to do a minus to all the x's. So this is one of the transformations that you need to do the opposite. If you don't do the opposite, it's going to shift the wrong way. Plus needs to go to the left, which means you need to make it smaller. Minus needs to go to the right, which means you need to make it bigger. So you look at your problem. Look at what's been added or subtracted inside the parentheses. That's called the argument. And then do the opposite. So we're going to study 4 transformations. 2 of them do the opposite. 2 of them don't. So somehow you have to remember which 2 are the opposite and which 2 are not. I'm telling you, this one's the opposite. And then we'll go back to the problem I showed you, and we'll do that one. Doing a problem involves 2 things. 1 is making a table of numbers. 2 is sketching. We'll start with the table, and then we'll do a sketch. All right, so we want to graph sine of x minus pi over 2. All right, so this is the first one we're doing. I'm going to write down the original table right here so I can see it, and then I'll do the new table. This is going to be the original. Can somebody tell me, for my graph of sine, what are my original x values? Yep.
0, pi over 2, pi, 3 pi over 2, 2 pi.
Yep. Those are the original x's. And what about the original y's? What are those?
0, 1, 0, negative 1, 0.
Perfect. That's my original table. Now we're going to make a table for the new graph. Okay, first thing is copy down the ones that are going to stay the same. We know that we're shifting left and right because we're subtracting inside the parentheses. So, what values there are going to stay the same? Yeah?
Y's.
The y's. Unfortunately, the y's are the easy numbers to work with. The x's are the harder ones, but this time we have to work with the harder ones. So the y's stay the same. And if you get those 5 values right, you would automatically get 5 points for this problem. Each number in the table is worth a point. So in this kind of problem, the table is worth 10 points on the test. There's 5. Okay, the other 5. So what I'm going to do is put the originals off to the side. I'm leaving myself some space because I'm going to do some arithmetic over here. First of all, am I going to add or am I going to subtract something to all those x values? Yep.
Add.
Yep, we're going to add. We're adding because we want to move all these x values to the right. How much do we want to shift all of those x values by? Yep.
90 degrees.
90 degrees, or in this case, pi over 2. So we're going to add pi over 2 to all of these. That's going to shift them all to the right by pi over 2 radians, or 90 degrees. Oh, actually, how about this? Okay, all my final answers will be in that table. Yes?
Why are we doing the opposite to, I know that's what we're supposed to do, but why is that?
Because when you subtract inside parentheses, that shifts your graph to the right. And if you want to shift something to the right, you have to add to your x values. Okay, so the first one, that's pretty easy. 0 plus pi over 2, just pi over 2. Pi over 2 plus pi over 2. Well, you need a common denominator. We already have it. What's 1 pi over 2 plus another 1 pi over 2? Before you reduce it. Yep. Yep, it would be 2 pi over 2, which as Anthony, was that you that said it? Pi?
Yeah.
Yep, which is just pi. I wrote it as 2 pi over 2 for a minute because I want you to see something when we're done. Okay, let's look at this one. Pi over 1 plus pi over 2 doesn't have a common denominator. What's my common denominator between 1 and 2? What is it? Common denominator can't be smaller than any of the individual ones. It has to be at least as big as the biggest one, sometimes bigger. Yep. 2. So what are you going to multiply the top and the bottom by to make them both 2's? Yep.
2.
Just 2. So now the problem is 2 pi over 2 plus 1 pi over 2. How much would that be? Yep.
3 pi over 2?
So 3 pi over 2. Next one already has a common denominator. Can somebody tell me what 3 pi over 2 plus 1 pi over 2 is? But don't reduce it yet. Yep.
4 pi over 2.
4 pi over 2. And now what does that reduce to? 2 pi. So look at the pattern so far. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. What do you think the last one is? Yep.
5 pi over 2.
5 pi over 2. And if we did another one, which we're not, it would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2. The numerator just keeps going up by 1. When you reduce it, you don't see the pattern quite as nice. That's why I put it here. But you should always reduce it in the final answer. And that's your table. So this would be worth 10 points on the test. Like 10 points out of how many points are on the test. Any question on the table? Yes.
Is that to plot new points?
Yes. Now we're going to plot those points. So we want to label our axes. If you don't put labels on your grid marks, what do grid marks normally go by? If they're not labeled, yeah?
1.
They go by ones. Well, if you look at these as decimals, that's 3.14. This one is 4.71. This one's 6.28. Those are not nice numbers to have to try to graph. So the only rule when you're labeling an axis is that you are consistent. You can use any labels you want as long as they are all equally spaced. So I mean, you could do something like this. That's fine. As long as the gap from one to the next is the same. What you can't do is this. That's wrong. Because now you're saying that the gap here is 1, then the gap here is not 1, and then it's not 1, and it's not 1 again. So we have to be consistent. When we started, all of these x values were how many degrees apart from each other? Yeah?
90 degrees.
They were all 90 degrees. And we took all those points that were all 90 degrees apart, and we shifted them all to the right, just like that. How far apart are they now? Since they all shifted together. Yeah?
Still 90.
They're still 90. All of these points here are still equally spaced because they came from points that started out equally spaced and they all moved together. So what I would do is when I label my x-axis, use these values because not only are they equally spaced, but it's going to give me a point that lands nicely on the lines, not in between lines. So we do need to label these. 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. So that's my x-axis labels. Make sure you put them low enough so you have room to draw and you don't draw through your points. Technically, you don't need to do what I just did there with the 1, -1, and 0. If you don't label it, I'm going to assume you're going to go by ones. You can label it. All right. And now plot those points down below. Let's see if I can. Not quite. So pi over 2, 0. Pi, we're at 1. 3 pi over 2, back to 0. 2 pi, -1. And 5 pi over 2, back to 0. Now remember, this is a wave. So try when you sketch it, try not to make anything that has like a sharp, like a point in it. So it should be, everything should be nice and smooth. So that is the new one. This, you don't have to do the original this time. I'm just showing you where the original would have been. You only have to draw what I have on the board. The original would look like this. Started right about, it's not perfect, but right about there. So the original would have started at the origin. This one has been shifted to the right. And what we say is these two graphs are pi over 2 radians out of phase from each other. That means it's like they're off from each other 90 degrees. And that's it. So the table, that would be worth 10 points. And then the sketch, this would be worth 2 points. Any question on the table or sketch? Out of the 2 transformations we're doing today, this is the harder one because of the arithmetic and having to find a common denominator. That's what makes this one a little bit harder. When we start adding and subtracting a number to the y's, that's easy because they're already numbers that are not fractions, so we don't need common denominators. All right, let's try this one. So this is a cosine function. And this time we're going to shift it pi radians. So this is twice as much of a shift as the last problem. The last one was pi over 2. This one is pi. So it's going to move even more. And because it's a plus, which way is the graph going to move? Yep, it's going to move to the left. And when we move things to the left, what happens to the x value? Think of a coordinate moving to the left. What would be happening to the x?
It'd be going down.
It'd be going down. Yeah, whether it's negative or positive, we don't know, but it'd be going down. Right? So to make something go down, you need to subtract something. That's how it's going to go down. We're going to be subtracting pi. What are we subtracting it from? The original x values for cosine. Can someone remind me, what are my original x values for cosine? Yep.
Are they the same as sine?
Yep.
So 0, pi over 2, pi over 2, pi.
Yep. 2 pi. Okay, so there's my original x's. Now, the y's stay the same, because we're not shifting up or down. We've got to be careful. What are my original y values for cosine, not sine? Lucas, can you tell me what my original y values are for cosine?
0 for cosine.
Cosine.
1, 0, negative 1, 0.
So yeah, 1, 0, negative 1, 0, and then 1. Yeah. Okay, now we just need to figure out what's going to go on. After I do enough x values that I see a pattern, I just go with the pattern. Right? But if you don't see the pattern right away, you might have to do a couple of them. So the first one, 0 minus pi, well, that's just minus pi. Okay, the next one, pi over 2 minus pi over, there was nothing there, so it's over 1. What's my common denominator between 1 and 2? Oh,
2.
2. So what would you multiply the top and the bottom by?
2.
2. Let's fix that. So now I have 1 pi over 2 minus 2 pi over 2. How much is that? Yep. Well, you have 1 take away 2, so it's definitely going to be a negative.
Pi. Sorry.
Well, we already have negative pi up here, and if you ever get the same x value twice, something's wrong. Because they all have to be spaced apart evenly, so we can't have 2 that are the same. Yep.
Negative pi over 2.
Negative pi over 2. When you subtract, your denominator stays the same, and all you have to do in the top is 1 minus 2. So negative 1 pi over 2. Pi minus pi, how much will that one be? Yep, that's going to be 0. Okay, next one. Do the same thing we did before. Common denominator is 2. What's 3 pi over 2? Take away 2 pi over 2.
Pi over 2.
Pi over 2. And 2 pi, take away 1 pi, is 1 pi. So there are your x values. Questions on those? All right, so now let's graph. Yeah, these aren't great numbers to have to graph if you go by ones. Right? You got negative 3.14, positive 3.14. So we're going to label our x-axis using values that are equally spaced. And we're going to use those because they're all equally spaced. Okay, so how much negative do I need? 2 negatives and then 2 positives. Okay, so let's start here. Negative pi. Negative pi over 2. the axis always has to be 0. I don't know how well you can see it, but I tried to make it look a little bolder. You can't make the axis a number other than 0. Sometimes I see people do that, but the axis has to be 0. Same thing. And then pi over 2 and pi. Okay. And what I do to plot my points, because I don't want to have to keep scrolling up and down, you probably don't have that problem on your paper, but I just remember the y's. 1, 0, negative 1, 0, 1. Scroll down. 1, 0, negative 1, 0, 1. Now, when you look at that, you might think it looks kind of like a V shape. But remember, it's a wave. And what you're sketching is that part of it. So try to make it look a little bit curved. And there's your sketch. The original would have been 2 tick marks to the right, or 180 degrees, or pi radians. Any questions on? Okay. Now, the last one, I don't want to go through the whole thing, but what I want to do is show you what's going to happen to the x values and something you have to be careful about when you do your spacing on your graph. When you do this one, your x values are going to end up being negative pi over 4, 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Now, it doesn't matter that they're all over 4. Just look at the number at the top. Negative 1, 1, 3, 5, 7. Let's think how you'd space those on a number line. Well, first, let me ask the question. Does everyone agree that these are all 2 units apart? Okay. So they are all equally spaced, and the same thing up here. These are all equally spaced as well. Think if you had a number line. And you put 0 right there. Where would negative 1 go? Yeah?
Behind the 0?
And when you say behind, what do you mean?
Like 1 tick.
Back here?
No.
No.
And take left of the 0.
Yeah, just 1 to the left. All right, so negative 1, 0. And where would the 1 go? Yeah?
1 to the right of 0.
1 to the right. So now, is that the rule? We're going to put 3, 1 to the right. Where does the 3 go? Yeah?
So 2 ticks to the right of the 1.
It has to go 2 to the right. Why? Because this is 2. We're not graphing 2. We're graphing 3. And then 5 would follow the same rule, and so would 7. That's how your spacing ends up looking. Sometimes people put negative 1, 0, 1, and then they put 3, 5, 7, just all right next to each other. But you can't, for the same reason you can't here. Is there any question on why I spaced those numbers like that? So then when you put them with pi over 4s, it's the same thing. Negative 1 pi over 4, positive 1 pi over 4, 3 pi, 5 pi, 7 pi. That's what the spacing ends up looking like. So you end up skipping 1. Because, same reason you had to skip 1 when you did the numbers without pi. Right, but we can take a look at one of those tomorrow if we need to. But that's the answer. so that's shifting left and right. The last kind of thing we're going to look at is shifting up and down. All right, so shifting, remind me again, is that adding or subtracting? Or is that when you multiply?
No.
Add and subtract. Shift is always add and subtract. So a vertical shift is going to move it up or down. What do you think the difference is going to be here? If a problem like that is shifting left and right, what's going to make it up and down? It's still going to be adding and subtracting. Yeah?
It's going to be outside of the argument.
Right, it's going to be outside of the argument. Like this. And if you're wondering, why did I use a D? Well, we'll talk about that on Thursday, but it has to do with the order you do the transformations in if you had more than one. There's 4. Shifting up and down is the last one you always do. So this time, what you add or subtract is outside of the argument. The only way something can be a shift left and right is if the letter and the number are grouped together in parentheses. That's the only way it can be a left and a right. If it's not grouped exactly like what I just said, it's an up and a down. So how about this one? Sine of x plus 3. Would that be left and right or up and down? Yep.
Would be up 3.
That would be up 3. What if I did this? Yep.
It'd still be up 3.
It would still be up 3. If I did that? Yep.
It's still up 3.
It's still up 3. Only way it can be left and right is if you had that. Now that is a shift. Well, specifically, it's left 3. Okay. Now, this is a transformation where you don't do the opposite. So if you see plus 3, which we just did, plus is up, minus is down. Don't do the opposite. We haven't done the opposite all year when we've done vertical shifts. Okay, so we are going to move either up or down. What, if you think of a coordinate moving up and down, what part of the coordinate is affected by up or down? Yeah, the y coordinate. So this means the x's are going to stay the same. Whenever the x's stay the same, that's great. Because the x's are harder to work with. You do not have to work with the x's when you go up and down. So I can tell you the x values for every problem we do in this part of the section. 0, pi over 2, pi, 3 pi over 2, 2 pi. X's do not change. And the y's are changing, but those are easy because the original y's are just 1s, negative 1s, and 0s. So all you have to do is add or subtract a number from a 1, a negative 1, or a 0. Very easy arithmetic. No common denominator. How do you know whether you're going to add or whether you're going to subtract? Well, you look at the original problem, and you do exactly the same thing you see in the original problem. Don't do the opposite. Some people on the test do the opposite. I don't know any other way to tell you. Just don't do the opposite. Just do exactly what it says. And you can put that on a reference sheet so you don't forget. So put it on there. Don't do the opposite. Okay, so when we're doing a vertical shift, do we do the opposite? No. Don't do the opposite. Okay, first of all, is this a shift left and right, or is this one a shift up and down? Yep.
Up and down.
This is up and down. You do not have that. That's the only way it can be left and right. I don't care where else you put parentheses. It's got to be just like I showed you to be left and right. All right, this is up and down. Okay, up and down, x's are going to stay the same. Quinn, can you remind me again, what are my original x values for cosine?
Cosine 0.
Yep.
Pi over 2. Pi. 3 pi over 2. And 2 pi.
Now, off to the side, I'm going to put the original y's and then leave a little space to do some arithmetic. And my final answer is going to go right there. Okay, what are my original y values for cosine? Yep, starts at 1.
0.
Yep.
-1. 0.
Okay. And what are we going to do to all those y values? We're going to shift them all by 2. But am I going to add or subtract? Yep. Add. Don't do the opposite. So I'm going to add 2. And once you do that, that's it. Those are your y values. 3, 2, 1, 2, 3. Very easy arithmetic on this. All right. Any question on how we got that table? All right, so now we're going to graph it. This time, leave enough room that you can go up higher, because you have to go all the way up to 3. So I set my x-axis and y-axis up so that I'm only in quadrant 1, because that's all I need. Now, if it went a lot higher than 3, like say we shifted it up like 20, well, then I might have to think about scaling these a little bigger. Maybe I'd go by 5s or something like that. But 3 is fine. And then this is 0, pi over 2, pi, 3 pi over 2, 2 pi. And plot difference. So 0, 3. Pi over 2, we're at 2. Pi, we're at 1. 3 pi over 2, now we're going back up. 2 and 3. As I said before, just try to make it look so it doesn't have any like points in the graph. Just like that. And that's your original function shifted up 3. Any question on the sketch for that? So that's a cosine shifted up. We'll finish up with we'll do a sine and we'll shift it the other way. Sine shifted down. Okay. So Chris, what values are going to stay the same?
The x values?
Yep, the x values. And hopefully you're starting to remember what those are a little bit. And how about y? What are my original y values for sine?
1, 0, -1, 0, 1.
Okay, if you put those here, you would be graphing cosine x minus 3.
Would it be 1, 0, -1, 0, 1?
minus 3.
I think that's what you said the first time. So for sine, it doesn't start with 1.
0.
Yep.
0, 1, 0, negative 1, 0.
Yes. Okay, so in something like that, you'd still get half credit because you got all the x's, but you'd lose all the y's, and that means you probably have the wrong sketch. Okay. Whoops, I meant to put those off. I should have put those off. So those are the originals. And why you already said what to do with all of them. How are we going to adjust them?
Subtract.
Yep. So don't do the opposite, just subtract 3. And Eileen, if I subtract 3 from all of them, can you tell me what I get?
Negative 3.
Yep.
Negative 2. Negative 3. Negative 4. Negative 3.
Good. So there's our table for the sine function shifted down 3. And now we'll do our sketch. So I'm going to label my x-axis. I'm going to put the labels above the axis because I know that I've shifted down. So my sketch is going to be below. So put the labels above. I'll make this one bold so you can tell it's the axis. All right. Also, we need to go down to negative 4. I got plenty of space, so I'm going to go. And my x-axis labels, I'll put them up here. Doesn't matter where you put them, just try to put them somewhere that they're out of the way. All right, 0, negative 3, negative 2, pi back to negative 3, and then negative 4, and back to negative 3. And then draw your cycle. And that's it. Any questions on it? Okay, so in the homework, that's pretty much what you'll be doing. You'll be graphing. What I'll probably have you do is, like I did on this one, the first one I did, I'll have you graph the original, and I'll have you graph the new one. Once you graph the original one time for sine and one time for cosine, then all the originals are the same. But so it doesn't look confusing, I'll give you 2 separate graphs if you use the worksheet. Oh, that's right, we're not using the worksheet on Schoology. So you can grab a piece of graph paper if you want it, or you can just use line paper and just draw some verticals in. Whatever's easier for you. All right, so those are the 7 problems to do for homework. So let's just put down. Okay, so 2 things I'm looking for. First thing is the table. In terms of points, that's the most important thing. 10 points for the table. And then I'm looking for you to sketch each one of those, just like we did, on paper. So the first 4 are phase shifts, and the last 2 are vertical shifts. Okay, so we'll go over that tomorrow, and then on Wednesday we will finish up the other 2 transformations we didn't do, which are the stretches. Stretching left and right, stretching up and down. Okay, so again, do not do the worksheet on Schoology. This is the one you want to do.